Hello guys, welcome back to ptet.chemistry channel. So if you have watched this topical video before as part of this topical playlist on reaction kinetics, you will know that this is actually slightly different from the previous video, and that's because usually I don't do corrections on my video. I just added in the video detail and the description info to basically inform you that I did make a mistake and I did do the corrections in the video details, but seeing as how this is a topical playlist and a lot of beginning learners actually use topical playlists to build out their concept, I feel that it is important that I actually address the issue, especially in a short video like this, which hasn't been viewed a lot. Okay, so hopefully going forward it will be useful to whoever use it in the future. All right, so that's my main reason for actually doing corrections on the video and re-uploading a new version of the video where I actually change my response to this question after someone actually take note of what I had done wrong. Okay, so I'll tell you what I done wrong. First of all, this is a graph of rate against time. Okay, rate against time. I think in my other video I actually make a mistake to say that it was concentration against time. So the theory was fine, but I did not produce a graph of rate against time. Okay, so let me get this right this time. So this reaction is called autocatalytic reaction. So one of the product catalyzes the reaction. Okay, so this is one of the famous case study stated in well, it's not really just on old syllabus, but it's also in recent papers. It's also in the Cambridge endorsed textbook as well. I remember reading it in the orange color textbook, which was the first edition for the, I think, around 2012 2013 printed edition, and then from 2016 syllabus onward there's a new textbook which is a blue colored one, is also in there. I haven't checked the latest one, which is the third edition, which is for the, I think, the 2022 exam series. I haven't checked the textbook yet whether they still have this or not, but I'm pretty sure they still do, because it's one of those things that that are quite worthy to be learned. All right, so let's get started. So your product acts as catalyst. So when your product concentration goes up, then amount of catalyst will goes up, and when amount of catalyst goes up, then your amount of reactant will go down much faster. That's because the reaction speed up, so it's a faster rate of reaction, so your rate will goes up, okay, and your reactant concentration will decrease much faster. This is a graph of rate against time. So at the beginning we can all agree that they start from 0 because no reactant, well, no product. Actually, it's not that not reactant, but no product at time 0. So no product at t equal to 0, therefore no reaction, rate equal to 0. In having said that, D is being crossed out. We now have 3 options. Now what do we know? Between A, B and C, A and B, they both stay constant there. You see that? Constant and constant. Whereas this one here, there is something that goes down. Okay, so which one makes most sense is that as the reaction progresses, you might expect as you get more product and more catalyst, then your reactant concentration decrease much faster. Then not much reactant is left. Even though you have a lot of product by then, because a lot of reactant has reacted to form the product, even though you have a lot of product which can act as a catalyst, but you don't have much reactant towards the end of reaction. When you don't have much of reactant left, then it doesn't matter how much catalyst you have, the rate will decrease because the concentration of reactant decreases slower. When you don't have a lot more reactant left, they are just not going to be catalyzed by the large amount of catalyst present, not to the extent when you have a lot of reactant, each of which can be catalyzed individually. All right, so the rate will decrease at the end, which means directly that A and B cannot be the answer. It has to be C. Okay, as you could see, okay, let me try and use another one. So if I draw a tangent, so this is a tangent at time equal to 0. The gradient, actually not the gradient because this is not concentration. Sorry, that was wrong. That was a wrong concept. Now the rate increases the rate increases until a top value. When a lot of catalysts come from the product can catalyze the reaction, so it goes faster, but it will go slower as a result of the reactant concentration slowly decreasing, and the rate will decrease again. I was talking about the initial rate because I was thinking about another graph, which was actually my mistake in the other video. So I'll just show it to you. Here, this is called concentration of reactant. Initially, your concentration of reactant will be high, but then what happened then is it will go down, and then after it goes down, okay, hang on, I don't want that. So it will go down, but after some time, your rate will increase suddenly because your product will make the reaction goes faster. So suddenly it will go very fast, and then it will go very slow again. Okay, so in this graph, you have a concentration against time. So I hope you can see this is initial rate. Okay, and then what happened then at a certain time? At a certain time, I can draw another tangent. So autocatalysis happened because the reaction suddenly goes a lot faster. Okay, so reactant concentration decreases so much faster. Rate increases. Okay, so I've written this thing in square bracket. It might not make sense right now in a reaction kinetics topic, but depending on your teacher, whether your teacher has covered chemical equilibrium before this, or your teacher will cover chemical equilibrium after this reaction kinetics topic, which you can also see from my topical playlist in topic 8, you will understand this square bracket is being used to denote or to represent concentrations in the next topic or in that topic really. Okay, so my mistake really was thinking about concentration against time graph, and this question is really about rate against time and not concentration against time. But remember, it can very easily have become a concentration against time kind of graph for this particular reaction, which is a case study. Okay, so from this question onwards, the remaining questions are all actually snippets from the previous tutorial video that I've done. So yeah, I had to do these corrections because I think it's important going forward for the future learners. All right, so apologies, and thank you to whoever actually corrected me in the other video, and hopefully the rest of the topical playlists are useful.
Okay, this question 2, they said that you have a piece of zinc, you react it with acid, and then you measure the volume of hydrogen. The zinc dissolves completely. So what does that tell you? Zinc completely reacts. So that means zinc is the limiting reactant. So that means H2SO4 is in excess. Just by reading the question, 2 reactant, 1 dissolved completely because it reacted completely. Okay, so our volume of gas, volume of hydrogen, depends on the limiting reactant, which is completely used up, depends on zinc. All right, so you have another piece of zinc, same surface area, same mass. Because of the same mass, then you will get therefore the same volume of H2. All right, so your total volume of H2 will be no change because your zinc was limiting and you use the same mass of zinc, so your volume of H2 will be the same. Your surface area is the same, so that means we cannot be thinking about any difference in surface area. But you have 40 cm³ of the same solution of dilute sulfuric acid. So you use even more of the same solution. That means same concentration of H2SO4. So it's not like your concentration has increased. So concentration is your mole per dm³. So in 1 dm³ of the H2SO4, you still have the same number of mole because you use the same solution. It doesn't matter how much more of the acid you use. The acid is in excess, so it's not going to affect the volume of your hydrogen evolve. Okay, but what happened to the initial rate of reaction? Well, you have same surface area, okay, on the solid, and you have the same concentration. Okay, so same concentration of acid, same surface area of zinc. There will be no change on the initial rate at all because it's not like you're using final powdered form of zinc. It's not like you are using more concentrated or less concentrated of the sulfuric acid. Therefore, there will be no change in the initial rate of reaction whatsoever. Okay, so this question has two things: what is completely reacted and what is not, and also what kind of factors will affect the rate of reaction. Concentration, surface area are amongst two of the things that we always talk about ever since your O-level or GCSE year, yeah? Okay. And this question 3, they said that the rate of a typical reaction roughly doubles for every 10 degrees Celsius increase in temperature, okay? So we know temperature is a measure of kinetic energy, which is dependent on the, which give you the speed of the reacting particles. So we know that as temperature increase, your particles move faster, your reacting particles move faster. So that is to do with collision frequency. Okay, so in theory you talk about collision frequency increase, but a lot of people forget that temperature also changes your Maxwell Boltzmann distribution. So this is the number of molecules with energy E. If I have higher temperature, my Maxwell Boltzmann distribution would change, and then I will have greater area under the graph of the molecules having enough energy to react. So actually what happened is the number of molecules with energy greater than or equal to the EA will increase. Therefore, we said that greater proportion of effective collision. So these two explanations are independent of each other, and they usually have to come side by side together when you explain why temperature increase rate of reaction. Yeah, so we need to not just talk about the number of collisions, because just because you collide does not mean you will react. Okay, so essentially collision frequency increase can increase the rate of reaction, but it does not necessarily mean that they will definitely react. It's essentially this bit that is really important. It's the proportion of effective collisions. So it's the number of molecules having energy greater than or equal to the activation energy that actually doubles your rate when you doubles the temperature. Okay, so that proportion doubles then. Okay, so that is actually the more dominant important factor. So now I just talk briefly about Maxwell Boltzmann distribution diagram just now. So they say which one represent the distribution of molecular speed at 500 K. This is higher temperature. So the dotted line is for lower temperature. So a dotted line is lower temperature. So as you can see here, they have the same maximum there, and that is automatically wrong already. You've seen in my previous Maxwell Boltzmann, when they shift to the right at higher temperature, they will drop down. Okay, because you distribute more of the molecules, you skew it to the right. There are more molecules with high energy. Therefore, there are less molecules having the average energy. Alright. Dotted line is lower temperature. So here, as you could see, the dotted line is further to the left. It should have higher fraction of molecules having that average speed. Yeah. So B is again wrong. D is wrong because going that way is higher temperature, whereas dotted line is lower temperature based on the information given in the question. Okay, and that is correct for C, because at higher temperature your distribution skew to the right, your maxima will decrease in the y-axis value because you spread more molecules towards the right, you skew it to the right. Okay, so that's the statistical term, you skew it to the right. All right. This last question for these short tutorials on the topical MCQs on rate of reaction or reaction kinetics, they're asking for what is the reaction pathway that will proceed most rapidly. That means the fastest. When we look at the fastest from enthalpy change diagram, we look for the one with the lowest activation energy, the one that is easiest to overcome, and therefore it will be the fastest. In terms of good yield, well, I can't tell you about this yet, but assuming this is equilibrium, okay, assuming if this is equilibrium, we will be looking at, if this is equilibrium, if we want good yield of the product, we want to push to the right, we want to favor the forward reaction. If we want to favor the forward reaction will let's see. Oh no, they all study at the same temperature though, so it's got nothing to do with equilibrium. I think I must be mistaken there. Let's see, what else can I talk about? Let's think about the activation energy first. Activation energy is from the reactant to the top of the peak. So from the reactant to the top of the peak. Okay, from the reactant to the top of the peak, from the reactant to the top of the peak. It turns out that I do not even need to know about the yield. I can see straight away the one with the smallest activation energy is C, and it does not matter what the rest says about the yield. The fastest reaction has to be the one with the lowest activation energy. So straight away C is the most sensible answer there. Okay, cool. So I'll leave it there, and then I'll see you in the next videos for more updates on these short tutorial videos on multiple choice questions. Quite a good recap for you to revise your chemistry concepts, not just for the Cambridge International Curriculum, not just for paper 1, but across the whole A-level chemistry curriculum as well, whatever boards you're doing. So please subscribe to the channel if you haven't, and then share the channel widely with your friends. Thank you for watching.